Hello guys, in this video we're gonna study about self-adjoint operators and Hilbert spaces. We start with the definition of an adjoint operator. So if I give you a T which takes you from your Hilbert space H1 to H2, now L H1 H2 means that it belongs to the space of all bounded functions between H1 and H2. Then T star is the unique operator in L H2 H1 with the property that the inner product of txy in space H2 is equals to the inner product of x and t star y in my space H1. And that's pretty much the definition. And let's now move to some propositions, some identities. We need to show that we need to prove this identity. Now the way we proceed to prove this one is I take this, start with this. So I have the inner product of x and s star y, which is t star y, which can also be written like this. Now I split it into two parts. So this can be written like this and this. I just split this term here into two parts. So now, because of the property of self-adjointness, I can write it as this. I can take the star and it becomes just s here. Similarly in this case. Now I join both of them again, s and t. So I get to this step. And then with the self-adjoint property, I can write this expression as this. I can consider this s plus t together as one operator and write it as s plus t star here and multiply it out again and I get this. So eventually I proved that s plus t star is equals to s star plus t star, and because of the uniqueness property. So what do I mean by unique? This property, I mean to say that given a t, so I'll look at the definition again. So t star is the unique operator in LH2 H1. So you give me a t in LH1 H2, then I give you a unique operator t star in LH2 H1 such that this property holds this property. Now we start with proving the second identity. I proceed in the same way again. I write that down as x times alpha star t star y, and then this is equal to alpha times x t star y is equal to alpha times tx y. Now if I take the alpha back in, I can write it as alpha tx y, which is nothing as t. Oh, I'm sorry, which is same as x alpha t star y. I'm sorry for the mess. So this is how we prove this identity. Now we skip identity number 3. We start with identity number 4. We need to prove that the norm of S is equals to the norm of S star. So the way we proceed with this is, so here we start with inner product of tx comma y, which is equals to x comma t star y. And now we put y is equals to t of x. Now, if I put y equals to t of x, this becomes inner product of tx dx, which becomes norm of tx square, which is equal to, which can be written like this, since norm of x square can be written as the inner product of x with x. Now, this can be written as the inner product of x with t star tx. I just took t to the other side. Now, norm of tx square is less than equals to norm of x. And I split this into two parts, so I can write it as norm of t and norm of tx. So this is less than norm of tx square. This quantity here is less than this. I just split it into three parts. And then I can cancel tx from here, and I can say that tx is less than equals to norm of x norm of t star. And the next thing I do is I take supremum over x is equals to 1. So I can write sup of, so we take the supremum over x equals to 1, the norm of x being equal to 1, on both the sides of this equation. Apply supremum x norm of x equals to 1, and then I can get from here, I can say that this is equals to the norm of t, which is less than or equal to sup norm of x is equals to 1 norm of t star x, which is equals to norm of t. And hence I can say that norm of t is less than equals to norm of t star. Now what I need to do is I repeat with the inner product of x and t star y, and I write it as tx y, and put x is equals to t star y, which would give me norm of t star to be less than equals to norm of t, and hence proved. So from these two things I can say that norm of t is equals to norm of t star. Now the sixth proposition goes like this. So we have norm of sx square. I can write it as this. Now I can take s to the other side, so it becomes s star x, s star sx. Then I can use Cauchy shorts to write it like this for every x belonging to h, so that norm of s square is equals to, this is again the usual definition of sup norm. Now this is less than or equal to, I can substitute this here. So when norm of x equals to 1, turns out to be like this, which again can be written in two parts. And norm of s star was norm of s, I proved it above, and thus it's norm of s square. And hence s star star whole norm is equals to norm of s square. And therefore also if I substitute, instead of s I write s star, so it becomes s star star, it becomes a star star, and it gives me the same result. Now the seventh one is an interesting one. I start with kernel of s is equals to the perp of image of s star. So By kernel of S, I mean all those elements in my space. So all those x belonging to H such that S of x is equals to 0. So I want to prove that they belong to image of S star perp. And kernel of S star is equals to image of S perp. So now I start like this. I start like let x belong to kernel of S if and only if S of x equals to 0, as we discussed. Now if S of x is equals to 0, then S of x comma y in a product would be equal to 0 for every y belonging to H2. So to keep in mind that my Hilbert's space, so like my operator in question S goes from H1 to H2. Okay, so it would be better if we write it here. So S goes from H1 to H2, and I can write it like this. Now again, since Sx is equals to 0, so it is the 0 element in my space H2. So if I take the inner product with any y belonging to H2, it would of course turn out to be 0. Now using the self adjoint property, I can take S star here for all y belonging to H2, and then I can say that x belonging to image of S star perp, because if you see, this is image of S star. So what is image of S star? Image of S star is, so S star goes from H2 to H1. So if I see image of S star, it would be giving me some element in my space H1. And now if I see that X, when I take the inner product with any element in my space H1, and if it gives me 0, then X must belong to the perp of the element in the space. So the idea is this element here belonging to image of S star. It belongs here. And if I take the inner product with X, every time it turns out to be 0, which implies that X must belong to image of S star perp. That's the basic idea. So if I write X S star Y to be 0 for every Y belonging to H2. Now this is image of S star. Okay, so image of S star, sum H1, say whole of this H1, and this is, say, image of S star. Now for every such S star Y, if the inner product of X with S star Y is equals to 0, and S star Y is an element in image of S star, therefore the inner product of S with S star Y, when it gives me 0, therefore I can say that X belongs to image of S star perp. Since, so this condition holds, I can say that X belongs to image of S star perp. Now it follows that X belongs to kernel of S. It implied if and only if X belongs to image of star perp. So my result is proved. And if I replace S by S star, the other result is also proved. I'll go through the corollary. So let H1 and H2 be Hilbert spaces. The operator S from my space H1 to H2 is injective. If and only if image of S star is a dense subset of H1. Let H1 and H2 be Hilbert spaces. The operator S from H1 to H2 is injective if and only if image of S star is a dense subset of H1. So as to say that H1 is, this is what I mean to say. Now we know that the projection theorem says that let V be a closed subset of H1. then H1 can be written as V hot cross bun V perp. Now, so I know that image of S star is a subspace of H1. And in order to use the projection theorem, what I do is I close it, because projection theorem can only be used in the case of closed subset. So I close it and I can write H1 as image of S star. It would be better if I give some reference and I say that H star goes from H2 to H1, and therefore image of S star. So I can write H1 as this. Now the perp of anything is closed. So W closed perp is equals to W perp. This is the standard result. And therefore I get the second line from this, and then I can see that the third line, that image of S star closed hot cross bun kernel of S. So I replaced image of S star perp with kernel of S because of, so this is because of this here. If you can remember what we did here. And my theorem says that operator is injective if and only if kernel of S is equals to 0. So if kernel of S is equals to 0, then H1 would be image of star, because kernel of S is 0, and then image of S star is a dense subset of H1. I say that S is injective if and only if kernel of S is equals to 0, and when kernel of S is equals to 0, if and only if H1 is equals to image of S star closed, closure of image of S star. So there we are. Let me repeat once more what we did in this corollary. So we had an operator from S, an operator S from H1 to H2, and S star goes from H2 to H1. So I used the projection theorem. I said H1 is equals to V hot cross bun V perp, where V is a closed subset. So I closed my image of S star close. Then I did this operation, I did this operation, I did this operation. And from here, as soon as I got here, I can say that operator is injective if and only if kernel of S is 0. And if kernel of S is 0, if you see in this case, then H1 is equals to image of S star closure. So image of S star is a dense subset of H1. There we are. Now the next definition is, let H be a Hilbert space. The operator T is self-adjoint if T star equals to T. So I can write for self-adjoint, I can write, now let's see the examples. Now let's look at the examples. So I have a Hilbert space H, which is given by Cn. And now T is represented by the matrix A. And T star is represented by the matrix A complex conjugate transpose. The self-adjoint operators on Cn are therefore precisely the operators which are represented by Hermitian matrices. So if I have in my space H Ax in a product P, then it is equals to X A complex conjugate transpose P in a product. So that's the usual definition of self-adjoint operators on Cn. So the next thing that we're going to do is this example. Let L and R be respectively the left and right shifts on L square, which is the L2 space. Now observe that the inner product is defined by this formula. We have already seen that in the previous video. Now if you just write out the equations, how X looks like and how Y looks like, this should be capital X. and this should be capital Y. And yeah, so that is a sequence. This is a sequence, and the left shift is this. If you write it out, and the right shift looks like this, you just shift everything towards the right, and then when you just write the inner product, it comes out exactly to be this. You can just check for yourself, and that's pretty much it. So the L star equals to R. These operators are therefore not self-adjoint.